Okay, so we're now going to look at section 4.4 and talk about the fundamental theorem of algebra. We are going to, in this section, merge together a lot of the concepts and ideas that we've learned about polynomials. And we're going to look at being able to sketch a final graph for what that polynomial function looks like. So we've got a couple of terms and theorems that we need to talk about first. We're going to summarize the best we can as we go. The first one is the fundamental theorem of algebra. This says that if you have a polynomial of degree n, as long as your degree is greater than or equal to 1, then you are guaranteed to have at least one zero. So what this is saying is that if you have a function like x squared plus 2x plus 7, and your degree, which remember is your highest exponent, is greater than or equal to 1, you definitely have a 0. All right, you might have more than 1, but you definitely have 1. Now, it does make the note that the 0 might possibly be a complex number, which means it would have an I, an imaginary solution, which means it may not show up on your calculator, but it does, in fact, have a 0 at least 1. All right, we have a linear factors theorem. This one says that if you have an nth degree polynomial, you should be able to factor it as a product of n linear factors, which means that if you have a polynomial that looks like x squared minus x minus 12, that it should be possible for you to factor, if this is degree 2, into 2 factors. And we know that that is the case because we can factor that one. Now I'm doing a square just because it's easy to work with, but the same rule would apply if it was a third power or a fourth power or a fifth power, that the degree should match up to the number of factors that you have. Okay? We also have a rule that says that if your degree is n, that you have at most n x-intercepts, and remember an x-intercept is the same thing as a 0, so they really could have said zeros here. And at most n plus minus 1 turning points, which means that if your polynomial is x to the third minus x squared plus 4x minus 7 with a degree of 3, that you have at most 3 zeros and at most 2 turning points. Now remember, a turning point is a place where the graph changes direction. So if it was going up, it would start to come down, or vice versa. We also bring in the idea of multiplicity, which says that if you have a linear factor that occurs more than 1 time or more than 0 times, we say that it has a multiplicity factor. Okay, so what this is saying is that if you've got a polynomial function and say it is factored, okay, so what this really means is that some of these terms occur more than once. So the x plus 2 is okay. The x plus 1 squared really means that it's x plus 1 times x plus 1. And the x minus 3 cubed means x minus 3 times x minus 3 times x minus 3. So what this is saying is that when you go write your zeros, you actually have 6 zeros because you have 6 factors. You have negative 2, you have negative 1 and negative 1 because that occurs twice. And you have 3, 3, and 3. However, we don't normally list out duplications like that. I mean, normally if you're working a problem, you're going to list out negative 2 as a 0, negative 1 as a 0, and 3 as a 0, and leave it at that. But we can talk about the multiplicity, which tells me how many times those zeros occur. So you could then go forth and say that if I wanted to look at multiplicity, the negative 2 is only 1 time in the list, the negative 1 occurs twice, and the 3 occurs 3 times. Okay, and notice that those multiplicity numbers correspond to your exponents on the terms. So like on the 3, that's the exponent. Tells you how many times it occurs, tells you what the multiplicity is. All right, and furthermore, it matters whether that multiplicity is an even number or an odd number, because that gives you some indication of what's happening on the graph. So if the multiplicity is odd, then we expect that the graph is going to cross through the x-axis. So that tells me that here, that the graph is going to cross the x-axis at -2, and that it should cross the x-axis at x is equal to 3. And so what happens if it's even? If it's even, it stays on the same side, which means it basically comes up and it touches the x-axis, but it doesn't go across. So in our problem, we would expect the graph to touch the x-axis at -1. But not cross. All right, so we're going to take this problem right here and we're going to work on it in a little more detail. All right, so we'll come back to what we just did in just a second. We want to sketch the graph of the polynomial, so we want to kind of think about what we know. We know that the degree of the polynomial, all right, I'm coming back over here, that the degree would be 6. Because if I start multiplying this thing out, all right, so if I take it right here, and I multiply it out, I multiply the first terms together, I'm going to do x times x times x times x times x times x, and that's going to be an x to the 6th, and that's going to be the highest power of x. So I know that my degree is 6. Okay, which means that I have at most 6 zeros and 5 turning points. Remember, we talked about that just a minute ago. Same number of zeros as the degree and 1 less on the turning points. Now, back in section 4.1, we talked about what happens on the end behavior of the graph. And we said that if the degree was even, which 6 is even, and your leading coefficient was positive, which we know our leading coefficient is going to be 1. Okay, on that x to the 6th. So that beginning term is going to be x to the 6th, and then we're going to have a bunch of other stuff behind it. All right, so our leading coefficient is positive, and our degree is even. Then we talked in section 4.1 about the fact that the graph would go up on the left and the right. Okay, so that gives you some indication about your end behavior. Okay, so that's going to be helpful. We also know that we could find the y-intercept fairly easily. Now the x-intercept might be more difficult, but the y-intercept would probably be fairly easy to find. Well, the x-intercepts are the zeros, so we can do those as well, but the y-intercept is easy to find in terms of a calculation. So let's look at that for just a second. Remember that on the y-intercept, you're going to put zeros in for the x's. So we would say f of 0 is equal to 0 plus 2, 0 plus 1 squared, 0 minus 3 to the 3rd. So that's going to be 2 times 1 times negative 3 to the 3rd, which is going to give you 2 times negative 27, which is going to give you negative 54. So we know that the y-intercept would be 0 and negative 54. Now, like we said, the x-intercepts are the zeros, and we're going to do those kind of separately here. So we know, we've already done these actually. Let me go back over here. All right, so here we go. We've got the zeros listed out, and we've already talked about the multiplicity as well. So we've got that part done as well. All right, so let's take this information and let's try to put it together on a graph. Now, the book has already drawn the graph out for us, so let's just make sure that this makes sense. All right, so the first thing I'm going to do is mark those zeros on the graph. So I have a 0 at -2, -1, and 3. All right, and so I've plotted those 3 points. Here's the -2, 0, here's the -1, 0, and here's the 3, 0. So I've got those on there. All right, so now we have said, let's talk about the multiplicity part. We said that the graph should cross the x-axis at -2 and at 3. So at -2 and 3, the graph is going to cross. So that tells me this piece looks like that, and this piece looks like that. And we know that at the -1, it's supposed to touch. All right, so we know that it either comes down like this and touches or goes up like that and touches. And so we'll kind of leave that unknown for just a minute. I know my end behavior. I don't know exactly where to put it, but I know that it goes up. You might need to pick a couple of points to know exactly where. Okay, and we can plot out our y-intercept, which is down here at 0, -54. All right, so kind of to fill in what we don't know, you still may need to pick out a couple of values to figure out what the graph is doing. So you might somewhere off to the side still need to do kind of a t-table and pick some values. All right, so the book says maybe you pick out 1 and you plug that in and you get -96. So 1 and -96 is going to be down here. And maybe you pick 2 and you get -36 when you plug that in. So 2 and -36 is going to be right about here. And so you can do that enough that you can fill in the in-between pieces and get a sense that the graph looks like this. And so what we're trying to do here is basically just sort of put our pieces together, put the concepts together that we've learned, and be able to sketch a graph of that function. All right, so the next thing that we look at is what's called the conjugate root theorem. This says that if a minus bi is a 0, and I'm just summarizing here, all right, then the conjugate, which is a plus bi, is also a 0. It has to be by this theorem. So it says that if you know one of them, you definitely know the other one if you're talking about a complex number 0. All right, so our example on this says that if we know that 4 minus 3i is a 0, they want us to factor this polynomial completely, and our polynomial looks like x to the 4th minus 8x cubed plus 200x minus 625. Okay, so I know if the degree is 4 that I'm really expecting at most 4 zeros. I know that one of those zeros is 4 minus 3i because they gave me that one. I know that 4 plus 3i is also a 0 because of the conjugate theorem that we just looked at. All right, and I am expecting to have 2 more zeros because the degree is 4. All right, so how do we do this? We use the techniques that we learned before. If we know 1, 0, we're going to start with that 0 and do synthetic division. So I'm going to divide 4 minus 3i into 1, -8. We're missing our squared term, so I'm going to hold that with a 0, 200, and -625. Okay, and so we're going to see what we get when we do synthetic division. So I'm going to drop the 1 down and multiply. So 4 minus 3i times 1 is 4 minus 3i. And we're going to add that to -8. So that's going to give me -4 minus 3i. Now, you may want to do this multiplication somewhere sort of off to the side. All right, I'm going to do it right here and then erase it. So I've got 4 minus 3i that I want to multiply by -4 minus 3i. FOIL method, first times first, is -16. Outside is going to give me -12i. Inside is going to give me +12i. And last is going to give me positive 9i squared. So these middle terms are going to cancel out. The I squared is going to become a negative 1. So I have negative 16 plus 9 times negative 1. Negative 16 plus a negative 9 is going to give me a negative 25. All right, and we'll add it to 0. We're going to get negative 25 on the bottom. All right, we're going to multiply again. So negative 25 times 4 minus 3i will distribute. So negative 25 times 4 is going to be negative 100. Negative 25 times negative 3i is going to be positive 75i. And we'll add. So we're going to get 100 plus 75i. And we need to multiply one more time. So I'm going to multiply 4 minus 3i times 100 plus 75i. All right, first times first is going to give me 400. Outside is going to give me positive 300i. Inside is going to give me negative 300i. And last is going to give me negative, let's see, that's negative 225i squared. So again, middle terms are going to fall out. We're going to put a negative 1 in for the I squared. So it's 400 plus 225, which is 625, which gives me 0. Okay, now that can seem a little tedious. You just need to be careful as you're doing that calculation. All right, so what we've done now is reduced that fourth powered polynomial down to a third power. We have another 0, so we're going to do the same thing. We're going to do 4 plus 3i this time. And we're going to multiply into the reduced, or we're going to divide into the reduced polynomial. So where we left off before, we're going to divide into that. All right, so we'll drop our 1 and we'll multiply. So 4 plus 3i. Notice here you're going to have 0 coming out of that. 4 plus 3i times 0 is 0. We'll drop down the negative 25 when we add. All right, and then we'll multiply one more time. Distributing that negative 25 is going to give me negative 100 minus 75i. And when we add these two together, we're going to get 0. So now reduced to a squared term. So what's left? We have 1x squared plus 0x minus 25 is equal to 0. All right, and x squared minus 25 is easy to factor. We know that that's going to factor into x minus 5, x plus 5, which gives me my 2 other zeros. Now, it asked me to completely factor, so now that I know my 4 zeros, I can set this up in factor form. So I can do a 0 for the negative 5, which will be x plus 5. I can do a 0 for the positive 5, which will be x minus 5. Okay, now the other two they work the same way, but they're just a little bit more tedious. So I'm going to do x minus, and in parentheses, I'm going to put my 0. We'll come back and we'll kind of clean that up in just a minute. And then we're going to do x minus, and we're going to put the other 0. All right, so we are going to have x plus 5 times x minus 5 times x minus 4 plus 3i times x minus 4 minus 3i. And I'm just distributing that negative through both of those parentheses. So there is my final answer in factored form. Okay, our last example asked me to construct a 4th degree real coefficient polynomial with zeros of 2, -5, and 1 plus I, such that f of 1 is equal to 12. So they're giving me the zeros and they're asking me to set up the polynomial. So this is fairly easy. We can do a factor for the 2. We can do a factor for the 5. Remember, you're doing opposites, so x minus 2, x plus 5. And then we can do what we just did. We can say x minus, and we can do 1 plus I. Okay, and so we're going to have x minus 2, x plus 5, x minus 1 minus I. We also know that if 1 plus I is a 0, that 1 minus I is a 0. And I'm already thinking ahead that if I leave it like this, I have a problem. Because when I look at my x's, 1x, 2x, 3x, this is a 3rd degree polynomial. We're supposed to have a 4th. So I have to think, okay, what did I miss? And I missed that conjugate pair. So we know that we also will have as a 0, x minus 1 minus I. Okay, remember that those complex numbers come in pairs. Okay, so that's going to take care of the 4th degree polynomial. We have the 4 zeros taken care of. The only problem is that we're supposed to have f of 1 equal to 12. And we're going to need a constant sitting out in the front so that we can be assured that that's actually going to happen. So I'm just going to put like an A here. And then we're going to make sure that we've got the right number there. If we don't actually need it, the A will end up being a 1 and we'll drop it anyway. But if we do need it, then we'll put the value in front. All right, so our next step is to try to solve for that A and figure out what that A is, and then we are pretty much done with this. Okay, so we are going to use the fact that f of 1 is equal to 12. Now, my problem with this is these i's. Okay, I'm going to have some difficulty plugging in and having an I left in the calculation. So I think what I'm going to do is I'm going to go ahead, and this is a little messy, but I'm going to go ahead and multiply these two together so that I don't have an I left in my problem. All right, so let's sort of go through this step by step and be sure we understand. We're going to multiply the x times all 3 of those terms. All right, so I'm just going to do it over here and then we'll put it where it needs to be. So x times x is x squared. X times -1 is -x. X times I is xi. Okay, and then we're going to move and we're going to do the same thing for our second term. So this -1 we're going to multiply by all 3 terms. So -1 times x is going to be -x. -1 times -1 is going to be +1. -1 times I is going to be -i. Alright, and then we're going to do the same thing for the I. So -i times x, -ix. -i times -1 would be +i. -i times I would be -i squared. Alright, so let's look at what we can cancel or what can combine. I've got an xi and an ix. Those are the same things, and one's positive, one's negative. I've got a -i and a +i. Those are going to go away. Okay, so let's look at what's left. I've got an x squared. I've got 2 x's. I've got a 1. And I've got, remember, this is a -1. So I have a minus a -1, which is another 1. So I have x squared minus 2x plus 2. All right, so x squared minus 2x plus 2. So let's take our function And let's rewrite it that way. So that way we don't have an I to worry about. And we can plug stuff in a little bit easier. All right, so now I am going to plug in my 1 and my 12, and let's see what we end up getting. All right, so I am going to put the 12 in for the f of 1. I'm going to leave the a, and I'm going to plug in the 1 for the x's. Okay, so I have 12 is equal to a times -1 times 6 times 1 minus 2 plus 12 would be 11. So I have 12 is equal to all right, so 12 is equal to, all right, hold on just a second. That is a 2, so I just made a careless mistake there. All right, so that should be a 2, which would make that, let's see, 1 squared minus 2 plus would be make that a 1. All right, so we're going to have -6 times a, so a is going to need to equal -2. All right, and so now I can come back up here, and in place of this a, I am going to plug in a -2. And we have our polynomial. Okay, now they may ask you to multiply it out. That's a possibility. All right, and so we'll just kind of look at some alternate ways to write the answer in factor form. You're going to have it like that. This is what we had initially before we multiplied anything out. If they want you to multiply the entire thing out, which hopefully we're not going to be asked to do that very often, we would get that expression there.